Okay, we're going to be solving logarithmic equations. There's a couple of different ones that you'll see, but they're all pretty, hopefully you'll find them not as scary as they sound. I know when people hear logs, they get a little nervous, but let's look at this one. We'll use log base 3 will be our first example. All right, so once again, I want you to come over here and imagine with me for a minute that this is the equation that I have. You ready? Let's say I have log base 3 of x is equal to log base 3 of 7. Well, what do you think that x has to be equal to? If you're saying 7, then you are saying the right thing. Obviously, since this and this are the same, this and this have to be the same. So if this and this are the same, what else has to be the same? This and this. Okay? So what am I going to do? I'm going to set those two things equal. All right, here we are. So now we have this expression or this equation, and all I have to do is figure out the x that makes it true. So the first thing I'm going to do is subtract x from both sides and get x minus 10 is equal to 7. And so x must be equal to 17. Now with logarithmic equations, there is one other thing that we have to check. If you remember, this expression inside cannot be equal to 0. And again, if you need to see the other video on domain of logarithmic functions, you can look at that one. But this expression and this expression, these expressions inside the logs, this one right here even, they never can be 0 and they can't be smaller than 0. So they have to be greater than 0. So what I want to do here is I want to figure out what numbers would make this one undefined. So what numbers can I not use? That's a lot of times how we talk about domain. Instead of talking about the numbers that can be, talk about the numbers that can't be. So hopefully you see here that x has to be greater than 7. Because if it were 7, it'd be 0. If it were, greater than 7. What am I talking about? Greater than negative 7. If it were negative 7, then it would be 0. And if it were smaller than negative 7, so negative 8 or negative 10, then we'd have a number that was less than 0. So this one has to be greater than negative 7. This one, maybe you don't know right off the top of your head, but what you can do is figure out what makes it exactly 0. So if I do 2x is equal to 10, x is equal to 5. So I know 5 is the number that makes it exactly 0. If I don't know if I want the numbers that are bigger or smaller than 5, then all I have to do is make my number line. And what I'm going to do is I'm going to plug in a number and see if it comes out bigger or smaller or, greater, bigger or smaller than 0. So I like to pick the number 0, as you know from working with me, that if I can use the number 0 as my substitution number, that's usually the one that I use because it's easy. So if I do 2 times 0 minus 10, we can see that comes out to be negative 10. And we said that that would be a no-no for this situation, right? We do not want that thing to come out to be less than 0. So this would be a big fat no-no. We could not have that one. So this is a no. I don't want those numbers over here. So that must mean that the numbers I'm looking for are on this side, but let's just check it out just to be sure. So let's put a 6 in there. That would be 12 minus 10, which would be a 2. Well, that would be okay. So here we want the numbers that are bigger than 6. Now let's take a look at the number that we got. Is it bigger than negative 7 and is it bigger than 6? It is. Then this is a number that I want to go with. And again, you could plug them in and make sure that they came out equal to make sure that it was the right number, not just that it is not extraneous. But so there we go, about 17. And this is what we do if we have two things with the same base on either side. We're just going to set those expressions equal because, well, that makes sense, right? Let's look at another one. Let's look at this one. Okay, so this one's a little bit different. For this one, I can't just set the two expressions equal because I have this one on this side. It's not a log equal to a log. And I can't just, put it in exponential form at the moment because it's we're adding two logs together here. So I'd have to take care of that situation first. But luckily, we know how to do that because we're very, very smart math students, right? So we can obviously use our log rules to condense this. And if you remember, when we're condensing two logs that are added together, what we're really doing is multiplying these expressions on the inside. So this is going to be log 3 of x times x plus 2 is now equal to 1. So let's go ahead and multiply this out. Log 3 is x squared plus 2x is equal to 1. Okay? All right. Now from here, again, it's not like the one above where I have two logs on either side, but I do know how to rewrite this one in a way that is helpful. If I rewrite this one as 3 raised to the first power, base 3 raised to the first power has to be equal to this thing, well, now it feels like something that's a possibility for me to solve. So again, I just made this one up, so I don't know how wonderful it's going to come out, but the joy is that since it's quadratic, we have tons of strategies to solve it if I don't really know what it is. The first one I'm going to just try is to see if it's factorable, because if it's factorable, that's what I would prefer to do, but if not, then we're going to complete the square or quadratic formula or some other method, graphing, or some ones that are probably not as easy. All right, so I need factors of 3 that are going to add up to a 2. So it does feel like it's possible, right? If I put a 3 and a 1, and I need one of them to be negative and one of them to be positive to get that negative, and I actually feel like we hit on one that is factorable, because this will give me a negative x, and this will give me a 3x, so that will give me the 2x that I'm hoping for in the middle. How do you feel about that? How lucky was that? Good thing I'm super smart. Okay, ready? Now we know what to do from here. We set each of these equal to 0. So x is equal to 1 and x is equal to negative 3. Now, I'm going to box these in, but I might have to cross them out in a second because we got to go back to the beginning. And sometimes I suggest that you do this from the very beginning so that you don't forget about it. Remember we talked about in the last question that we have to make sure that it doesn't fall outside of the domain of these logs, right? So we said that inside these logs, these values have to be greater than 0. So here I can see that x has to be greater than 0. There's nothing to figure out there. And this one, x has to be greater than negative 2. So let's go back to our numbers. I had 1. Come on, 1. Show up. There you are. And negative 3. So I'm going to put them here. X is equal to 1 and x is equal to negative 3. So let's keep going back. All right, so let's take a look at our numbers. Is x bigger than both of these? Sure, he's okay. All right, negative 3 is not bigger than either of these. So that means that negative 3 is my extraneous. So that means not really a solution. And that 1 is my only answer to this one. Okay? How do you feel? A little lost, a little confused? Don't get scared. You'll figure them out. Don't worry. It'll become clearer as you practice them. All right, let's just do, I guess, one more for fun's sake. All right, let's see. Do I have a good one in my book? Nah, I'll just make one up. How about log base 3 of x squared is equal to, I don't know, 10. Let's do that. Okay, here we are. All right, so this one, what I'm actually going to do is I'm going to use my log rules first. So I'm going to actually use my log rule to put this out at the front. And why am I doing that? Well, take a look. It's going to make it a little nicer to work with, because now I can divide both sides by 2. And this becomes log base 3 of x is equal to 5. Nice, right? Okay, now there's a couple ways you can think about this. You can think about it as putting in an exponential form, which is probably the way that a lot of you are thinking about it right now, because that's what we just did. We would say 3 to the 5th is equal to x if I put it in an exponential form. But we could also use our inverse function idea. So I'm going to use that idea that we talked about in the last video. Remember we said that if we have 2 plus 3 is equal to 5, then if I said 4 to the 2 plus 3, that would still be equal if I made this one 4 to the 5. Do you remember talking about that? And we talked about that if I had 4 to the log base 4 of x, this would actually be equal to x, because this guy says that I'm the value that you have to raise 4 to get x. So this is that idea that we talked about in that other video where we said if I compose inverse functions, and my inverse functions in this case are this one. So if I take this one and put this one inside, so I took this and put it in for x, I composed them. When you compose inverse functions, you should get out what you started with, if you remember. And again, if you can wrap your brain around the idea that I'm the number that you have to raise 4 to get an x. So if I raise 4 to me, I'm that number, whatever that number is, then x has to be the result. Okay? I'm going to do that same thing here. I'm going to use that idea here. I'm going to actually use the base 3 though, because base 4 isn't going to help me here because this is a base 3. So if I want it to be inverse functions, I'm actually going to stick a 3 on the bottom here. Okay? Why did I do that? Because now I know, just like here where we had the same base, these guys are going to like undo each other. Or sometimes I hear people say cancel each other out, which I don't like as much, but if that's the idea that sticks in your brain, so what's going to be left over is whatever is here. That's what it's going to be equal to. So it's going to be equal to whatever is here. These two things are going to undo each other, and we're going to have an x here is equal to 3 to the 5th, which of course is the same thing as if you had thought about it in an exponential form. So worked out the same. So x is whatever 3 to the 5th is, right? So 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is that 243? I want to say 243. Am I right about that? I hope so. So in this case, we found it out by using our inverse function idea, or changing it to exponential form. If you like to think about it that way, that's fine too. But the first thing that we did is we used our exponent rules to get this guy kicked out to the front so that we could kind of take care of him first and make our lives a lot easier. Now the last thing, of course, we have to check to see is if 243 is an okay number to use inside this log. So if I put a 243 in here, will I get a number that's 0 or negative? And the answer is no. So 243 is an okay number to use here, and we like him. All right, so that's solving log equations. Those are probably the most common kinds of things you're going to see. So try some out, and I'd be happy to hear from you if you're having trouble or you're stuck on any of these equations. Let me know.